Hey guys, it's Leah. Today we are going to go over section 2-5, graphing techniques and transformations. Please take a second to title your paper with this title and your name and the class name and the date. If you need to pause this video, please do so. Our first learning objective is to graph functions using vertical and horizontal shifts. So if you have your function, to give it a vertical shift up, you're going to add a value to your function, as long as that value is greater than 0. To give it a vertical shift down, you are going to subtract a constant value from your function. So I like vertical shifts because they're straightforward. It's shift up, you add it to the end, shift down, you subtract it from the end. Horizontally is a little bit different. If you look, horizontal shifts, you have to replace your x value with x plus your constant that you're shifting. So if you want to shift it to the right 5 units, you replace x with x plus 5. So, and I think of it as horizontal shifts are inside the function. Vertical shifts, the number happens outside of the function. So these ones are opposite. If you want to shift it to the left, so on the x-axis that would be towards the negative region, you would have a plus value. If you want to shift it to the right, you would have a minus value. All right, so for vertical shifts, we just add or subtract the value we want to go up or down. And for horizontal shifts, we replace x with x plus to go to the left and x minus to go to the right. All right, so let's look at this example problem. Please write down this function, f of x equals x squared. And we want to shift our parent function, so that we have x squared, g of x equals x squared plus 3. So on your paper, put your axes. This black function here is y equals x squared. And we are going to shift it 3 units up. You don't have to put this table, but this table tells the story. If I put -2 into my square function, I get out 4. But if I put it into this function, I would go 4 plus 3, so that takes this coordinate and moves it up 3 points. And it actually does that to every coordinate. So this is a vertical shift up of 3. Make sure you have this graph on your paper. You can keep the same graph for the next example problem. So our next example problem, we are going to take our same parent function, but we're going to shift it down 4 units. So we take our x squared and we minus 4. And what that does is it takes our parent. So you already have this graph written down. Go ahead and write this nice parabola that is shifted 4 units down. If you look, it takes all of our square function values and subtracts 4 from the output. All right, we can, just to reiterate, when you take your function and you add a number, positive real number, it shifts it up. When you take your function and you subtract a real number, it shifts it down that amount of units. So if you have your parent function, you add 2, it moves you up 2. Your parent function, you move it down. And this works for not just squares, but square roots, absolute value, linear functions. This works for every function. All right, so we're going to explore, using our same parent function of x squared, a horizontal shift. So we're going to take the x value in our parent function and replace it with x minus 2. So in my mind, I always think of it as inside the function. All right, so we replace the x squared with the x minus 2, and note the parentheses. If you don't include the parentheses, it is not an inside, you are not replacing the x with the x minus 2. So this will shift us, always opposite when we're talking horizontal, so it'll shift us 2 units to the right. And then let's see how that looks. To the left. So when I have an x plus 2, that'll shift this parent function 2 units to the left. So just to review what we looked at, a horizontal right shift is an x minus h inside, so we replace x with x minus h. And a horizontal left shift, we replace x with x plus h. And this works for all functions. So here's the example of the left. So just add this to your graph that we already have. X plus 4 moves it 4 units to the left. All right, we can combine both shifts. So if we have in this case, we'll have a horizontal shift 3 units to the left and a vertical shift 5 units down. So you start with your parent function, shift it left 3 units, moves that vertex over 3 units, and down 5 units. So now our parabola is over to the left 3 and down 5. All right, we're going to take a look at compressions and stretches. Here is the details, so take a moment, pause this recording, write this down. So when we are compressing or stretching, so if we take our a value, so any real number a, and we multiply it by our function, our entire function, it stretches vertically if a is greater than 1, and it compresses vertically if a is between 0 and 1. And I'll show you an example of that. So if we multiply our the interior of our function, so our x values. So if we replace our x value with a number times x, where our number is greater than 0, we multiply each coordinate by 1 over that a value. So that stretches our graph horizontally if a is between 0 and 1, and it compresses the graph horizontally if a is greater than 1. And this is the situation. So anytime you do something horizontally to your graph, you're doing it to the interior of the function. So you're replacing with x, you're replacing x with another value. And in this case, we're replacing it with a times x. So let's see how that looks. Our vertical stretch, so if we take our absolute value parent function, and this works for every function in our function library, and we are going to multiply our function by 2 to get g of x. So if you look, we start out with this absolute value function. I definitely want you to have this in your notes. A 2 multiplied by the function absolute value of x will stretch vertically our absolute value function. So it makes our function taller and skinnier. So I think this is makes our function more basketball player. Makes it tall and skinny. So go ahead and put this taller, skinnier graph above your absolute value graph and arrow that it's y equals 2 absolute value of x. All right, on that same graph, let's show the compression. So when I multiply it by a number that's between 0 and 1, it makes my graph, I call it flatter and fatter. So it gives it a squish vertically. So go ahead and add this y equals 1/2 absolute value of x to your graph. So you should have the tall and skinny one that gives you the vertical stretch, and you should have the short and fat one that gives you the vertical compression. All right, and that just summarizes. Now let's take a peek at what, if we take our parent function, absolute value of x, which is this bold one right here, and we are going to, this is a horizontal compression, so we're going to replace x with 2x, and it is going to compress or squish. So imagine you have two pinchers, one going this way, one going this way. It squishes this graph, so it's more of this graph happens in a smaller amount of time. And if we look at what this says, it says multiply each coordinate f of x by 1 over a. So it is, we're going to get a taller, fatter graph. And then if we take our function and replace x with 1/2 x, we are going to get a horizontally stretched. So it is tighter to the x-axis than the parent function. Okay, so a horizontal, if the argument x of a function y equals f of x is multiplied by a positive number, the graph of the new function y equals f of ax is obtained by multiplying each x coordinate of y equals f of x by 1 over a. A horizontal compression results if a is greater than 1, and a horizontal stretch occurs if 0 is less than a is less than 1. So we're going to multiply each x coordinate by 1 over a. And let's see how that applies here. So here is our vertical stretch. So here's our nice little trigonometry wave. And if we want to have a vertical stretch of 2, each of our points, so if you look, our intercepts stay the same, but our outputs are doubled. So instead of being pi over 2, 1, we are now pi over 2, 2. So it just makes this a taller graph. If you look at here, we have 3x, and our convention said if a is greater than 1, we're going to have a horizontal compression. So our graph is going to do more in a shorter amount of time. So we are supposed to multiply the x coordinate by 1 over a. So we take our x coordinate, pi over 2, and we're going to multiply that by 1/3, because a in this case is 3. So instead of having pi over 2, 1, we are going to have the same output. We're still going to have 1, but instead of at pi over 2, it's going to be at pi over 2 times 1/3, which is pi over 6. So same here. Our coordinate here is pi 0, so it's at over pi up 0. And we're going to multiply the pi by 1 over 3. So pi times 1 over 3 is pi over 3. So we're going to, instead of being at pi 0, we're going to be at pi over 3, 0. Here, 3 pi over 2, we're going to multiply that by 1/3 to give us pi over 2. So the same wave happens, it just happens 3 times as fast. So normally this would take us 3 pi on the x-axis to have a complete wave like this, but in this case it is happening by pi, so a third faster, compressing it horizontally. All right, we are going to then graph functions using reflections about the x-axis and the y-axis. And the takeaway from this learning objective is, and we've already done this, we've tested symmetries, we've done this process together already, so this should be familiar, and if it's not, memorize it so it becomes familiar. So we've got y equals, take our function and multiply everything by a negative. We'll reflect it about the x-axis. If we take our function and replace x with negative x, it'll reflect your graph about the y-axis. So let's see a couple of examples of those. All right, so if we have our parent function y equals x squared, and I multiply that by a -1, it just flips it about the x-axis. So go ahead and sketch this graph here. Make sure you identify your parent function and identify the reflected function. This works, you can do this with any function. So we're going to do this with the absolute value function. So the square root function. Y equals square root x is this function here. And if we replace x with the negative x, it's going to reflect it about the y-axis. So go ahead and make this sketch. All right, so we are going to do a series of transformations here. We're going to start with this blue function, y equals absolute value of x. We're going to shift it left 2 units. So this is our pink. This matches our pink function here. We're going to replace x with x plus 2. So then it becomes y equals absolute value of x plus 2. We're then going to shift it up 3 units. So that's this green graph right here. And we do that by adding 3 to our function. And then we're going to reflect it about the y-axis. So we're going to replace x with negative x, and that happens right here. We're still going to have the plus 2 on the inside of the absolute value and the plus 3 on the outside. So our end result is this red graph right here. So reflecting about the x-axis just moves it that same distance across, the y-axis. Reflect about the y-axis, so it moves it across the y-axis. If I was 2 units away from the y-axis here, I am 2 units away on the right-hand side. Okay, there is one more that I want to show you. I want to show you the combining graphing procedures. This is kind of an interesting one. We have to do a little shuffle with our equation to get our reflection done correctly. So if we look at this function, f of x equals square root 1 minus x plus 2, we start out with the square root parent function. And then because this is a positive 1 underneath the radical, we are going to shift it left 1 unit. So if this was a -1, we would shift it right 1 unit because it's positive. So we're going to table the minus x for just a moment. Because this is positive, we're going to shift it left 1 unit. The next thing we're going to do is switch the order. So instead of 1 minus x, we're going to have negative x plus 1. So this shows that, oh yeah, I'm shifting it to the left 1, and this shows I'm going to reflect it across the y-axis because it's like replacing x with negative x. So here I have my function, and I'm going to reflect it across the y-axis. So instead of being at -1, 0, it's going to be at 1, 0. This coordinate's still the same. instead of being at 3 comma 2, I'm going to be at negative 3 comma 2. So it shifts it across the y-axis. And then this plus 2 means we're going to have to move this whole thing up 2 units. And we get this function here. And that is everything from 2.5.